Welcome to Magnetized Labs. Today we are going to see the design of STM32 based current sensor module design in KiCAD. The board will be like this after the PCB layout. If you want to enhance your electronic design skill and knowledge on this board, please watch this video till the end. This is the block diagram of the project. I have used a STM32 microcontroller, a 4-channel op-amp IC, 4 different types of current sensing techniques, and an OLED display to display the currents measured by these sensors. I have used a Type-C connector for the power input of 5 volt, and I am converting that into a 3v3 through an LDO to supply STM32 microcontroller. The currents measured by these current sensors are fed through an op-amp IC to STM32 microcontroller for accurate current sensing. And this OLED display will display the currents measured by the different sensors. There are different types of current sensing methods available in the world. We are going to see a few types of current sensing in this project. What are the types of sensors used here? First one is Vinson current sensor. This is a split through hole design. You can put your wire into this hole up to 8 square mm and then you can press to lock it so that you don't need to cut your wire to measure the current. This is from Vinson current sensors. This is from Allegro Microsystems, and this is also from Allegro Microsystems, and then this is conventional shunt resistor method. We'll go to the schematics now. When it comes to the schematic, this is Type-C connector. I am taking the 5 volt power input from this connector, and then I am directly giving it to the LDO to convert it to 3v3 to supply STM32 microcontroller. I have given one debug LED and then 5 volt power LED. And these are all necessary decoupling capacitors for the microcontroller. 16 MHz crystal for clocking. This is a reset switch, and then this is USB data plus line pull-up. This is the programming connector, 6-pin header, and then all the different types of current sensor we are going to see. This is the one from Allegro Microsystems. This can measure up to 30 amps in contact sensing. So you have to allow the current to pass through this IC. You can measure the current through bidirectional sensing, and then this is an isolated sensing halleffectsensor based sensing. It will be accurate. 44 millivolt you will get per ampere. And then this particular current sensor IC has the fault output also. If it exceeds the 30 ampere limits, and then it will give active low, you will get 0 voltage output. Otherwise you will get 3v3 digital high, mentioning that the IC is working properly without any fault. This is also from Allegro Microsystem, but this is, this will be able to measure the current up to 100 ampere in contact sensing. You have to allow the current to pass through this IC. This is also Hall effect sensor based sensing, so it's an isolated sensing. You can also measure the current in both the directions. This is the conventional shunt resistor method. You can put a very less resistor in shunt, so you can measure the voltage drop across this resistor. As everyone knows, per ampere this will give 1 millivolt, so you can use op amp to amplify, and you can measure through ADC of the microcontroller. This is Vinson current sensor. This is one of the coolest sensors I have seen. This has the split through hole design. You can just open the mechanical design of the IC and then put the wire into it. Up to 8 square mm you can put, so it's very easy. You don't need to cut your wire. Just insert that wire into it and then lock it. You start measuring your current. This is also an isolated sensing. You can measure the current in both the directions. You can measure up to 35 amps. And the interesting part is it's a non-contact sensing. You don't need to cut your wire to measure your current directly. You can just allow the wire through the sensor and then you can start measuring the currents. All these sensors will give the voltage output, and then that is fed through this pump for accurate current sensing, and I am reading through the STM32 microcontroller. USB data plus and data minus signals are directly connected to the Type-C connector for any debugging purpose. Even you can program through Type-C connector if you have a USB bootloader firmware. Yeah, that's it about the schematic. We'll go to the PCB now. I think before going to the PCB, I will show the 3D view of it. Yeah, this is the 3D view. This is Type-C connector for power input and USB communication. This is power indication LED, 5 volt to 3v3 LDO, reset switch for microcontroller reset, STM32 microcontroller and its crystal. This is the programming connector. This is the OLED display, so we can directly display the current which are measured by the different sensors. all the 4 different types of current sensors. For this Vincent current sensor, we don't need a connector, so we can directly pass the wire through this split-through hole, and then we can log the mechanical design of it. And these other 3 sensors, I have given the same connector. So this is op-amp IC. All the different types of current sensing voltage outputs will be fed through this op-amp and to the STM32 microcontroller for accurate sensing. So that's it about the 3D part of it. We will go to the PCB now. Yeah, when it comes to the PCB, most of the current sensors are, in contact sensing. We have to allow the current to pass through this IC. So I have used the 4-layer stackup. And also for the USB data communications, we have routed the USB differential pairs as the impedance matched signals for matching the 90 ohm impedance. Then the 5 volt output from the USB Type-C connector is fed to the 3v3 LDO that is going to supply to the microcontroller, which is STM32. And then this is the crystal oscillator for this STM32 microcontroller, debug LED, and then this is a reset button. So we'll go a bit in detail. This is a 4-layer stackup. Many people have asked to, explain the PCB layout a little bit detail so that they will be able to understand. Yeah, first we'll come to the Vincent current sensor. So I have placed it at the edge of it so that you can easily route the wire through it. The output of the Vincent current sensor directly fed through this op-amp, and then op-amp is like amplifying the voltage input, which is from the Vincent current sensor, and is directly going to the STM32 microcontroller. And then the second one is shunt resistor. Shunt resistor is non-isolated sensing, so the current also we have to pass through this sensor. This output I am actually directly connecting to the op-amp, and then directly I am taking to the STM32 microcontroller. And then this third one is Allegro microsystem sensor. This is high current sensing up to 100 amps we can sense, but the restriction of the ADC value is maximum 3v3. Up to 40 amps you can easily measure. So the output of this Allegro microsystem current sensor is directly taken to the op-amp, and then that output will directly go into the STM32 microcontroller. And then the fourth IC, that is also from Allegro microsystems, in contact sensing, we have to allow the current to pass through this IC. Output is directly connected to the op-amp, and then it is directly connected to the STM32 microcontroller ADC pins. The programming connector for programming the STM32 IC, I have given the OLED display to display the currents measured by the different sensors. We'll go a little bit in detail about USB data pair for impedance matched routing. From here it is starting from these pins to these holes. It is in the first layer, and to cross I have routed through 4th layer, and the rest of the USB data communication lines are routed on the first layer. So the second layer is the stable reference for this USB data impedance matched pairs. Yeah, that's about the PCB. That is how the layout works. When it comes to the applications of current sensors, we will use in power monitoring and management, especially in battery management systems, motor controller and drives, power supply designs and inverter designs, renewable energy systems such as solar energy, wind energy, where you will get the enormous amount of current, you will have to measure it, and then electric vehicle for sure, fault detection and protection. Most of the current sensors are used to measure the current when it exceeds the current limit, industrial automation circuits, consumer electronics, and medical equipment devices. Thank you so much. If you have any doubts, please let us know in the comments.